Saturated ascent. In this video we're going to examine the physics of saturated ascent when we have condensation of liquid water or the formation of ice. So consider a saturated air parcel that consists of 1 kilogram of dry air and Rs kilograms of water vapor at an initial state P, T and Rs. The mixing ratio is Rs and not R because the parcel is saturated. Let's lift the parcel infinitesimally through a depth of atmosphere dP to a pressure P plus dP. The parcel will cool to a temperature T plus dt, and the mixing ratio will change from Rs to Rs plus DRS. So the parcel is saturated before and after the ascent, the lifting. So we keep the subscript Rs, and that DRS has condensed as liquid water. And so there's latent heat released as that's happening. So we have to ask the question, what do we do with the latent heat? And what do we do with the liquid water, considering our parcel of air? In the vapor to liquid transition, there's a couple of possibilities here. In the figure on the right hand side you can see dry ascent marked by the dry adiabatic lapse rate. You'll see that the other two profiles are versions of a saturated adiabatic lapse rate, and parcels moving along those cool more slowly with height because there's the release of latent heat as liquid water is realized. And we're going to assume that that latent heat is contained within the parcel, it's not lost to the environment. So the parcel cools more slowly. If the condensate, that is the liquid, is retained in the parcel, then we say it's a reversible process. That is, it's adiabatic. That means that if we ascend up that adiabat, liquid water is realized, latent heat's released into the parcel, but the liquid water is retained so that if we move back down that adiabat, we have that liquid water to evaporate. And so the parcel moves up and down in a perfectly reversible fashion. If the condensate falls out, however, precipitates out, then we have an irreversible process. We go back down the adiabat and we don't have that liquid water we had before. And so we refer to that as a pseudo-adiabat. You can see that the reversible ascent, the reversible adiabat, cools even more slowly than the precipitate because there's a heat content to the liquid. The liquid also cools as it rises, and that makes a contribution. Let's consider the reversible ascent A1. That's where the liquid water is retained. What happens when it freezes? Well, at temperature T equals 0, there's a phase change occurring, and so we get a hail jump. There's a rapid amount of warming because there's latent heat, a fusion released. And then you can see that there's reversible ascent above that, where the ice is said to be contained within the parcel. So what we're going to do instead on the QT log P aerological diagram is assume an irreversible ascent all the way up. So firstly liquid water precipitates out, and then the ice precipitates out as well, to avoid things like the hail jump and the complications due to the liquid water being retained. So what sources of energy do we have for the as we expand, rise and expand the parcel? Well, there's the internal energy as indicated by the temperature. So the environmental pressure decreases, the parcel expands to accommodate that, and so there's a decrease in the internal energy as work's done on the environment, and the parcel cools. But now there's latent heat of condensation and sublimation. So there's changes of phase. On the aerological diagram, we will use saturated pseudo-adiabats that assume that it's irreversible saturated ascent, whereby all the condensate rains out, so we don't have to worry about the heat capacity of liquid water, and there are no ice processes involved at all. So there's no hail jump. So what you can see here now is a typical QT log P aerological diagram. Marked in green are the dry adiabats, where the only source of energy is the adiabatic decompression, giving rise to a change in internal energy. And then the saturated adiabats include both that contribution but also the release of latent heat, and therefore parcels moving along the saturated adiabats cool more slowly than they do along the dry adiabats. thinking about that from an energetics point of view, if we write the full equation that gives us our energy budget, we've got the Cp dt minus alpha dp. That's a form of the first law, which gives us dry ascent. You integrate that and you get the first term. But then we have a term that involves latent heat from liquid to vapor, L subscript LV, and then DRS. So changes in the saturation mixing ratio of the parcel as it rises, and we assume that that's contained within the energy budget. That is, it's retained in the parcel. When we manipulate that top equation, and I'll leave that as an exercise for you, you get the equation inside the box. So CPD log of theta d represents the dry ascent, and then the RS LLV on T represents the contribution due to latent heat release. And so we can write then out in words that the saturated adiabatic lapse rate, which is the lapse rate at which parcels cool when they are saturated, is equal to the dry adiabatic lapse rate plus a latent heating term. That latent heating term depends upon the latent heat, of course, and the temperature at which that's happening, but very much on the actual amount of water vapor that's in the parcel. And so clearly then, if RS, the saturation mixing ratio, goes to 0, then the saturated adiabatic lapse rate goes to the dry adiabatic lapse rate. Here's a schematic that shows those kind of physical limits. So on the top left, we see right up the top left of a SKUT log P aerological diagram, the green solid line is a dry adiabat, and the green dashed line is a saturated adiabat. As you move up the saturated adiabat, more and more liquid water is condensed, so the total RS in the parcel decreases and it asymptotes towards 0. When it does that, the saturated adiabat approaches that of a dry adiabat in the upper atmosphere. In the bottom right, you can see a saturated adiabat compared to a dry adiabat, and you can see there's a large angle between the two, which makes the diagram very easy to use. But you'll also see too these skewed lines, the isopleths of mixing ratio, cutting across the saturated adiabat. So as you move up the saturated adiabat, it's indicating continued condensation, and so that line's cutting across decreasing values of the mixing ratio. It means the amount of water vapor is decreasing and the amount of liquid water is increasing.